In our previous lesson, we learned about the different operations that we can do with complex numbers. Today, we're going to be getting into sort of what the geometric interpretation of those complex numbers are. In what ways can we sort of see and visualize complex numbers? So, as we always do, before we get started, let's take a deep breath. And let's begin. So the thing I'm starting with first is a little bit silly, but I think it's a valuable starting place. We know that the real numbers, which are denoted by that symbol, these real numbers can be interpreted geometrically by plotting them on a number line. So a real simple example, we're going to start nice and easy, right? Plot these numbers on a number line, right? So you know that a number line is basically, we've got 0 in the middle, and the numbers sort of extend off this direction in positively, and they extend back this way negatively, right? And so the number 5 is right here. Yay, we found it. The number -3 is right here. Yay, we found it. And pi is, 3.14. It's, in there somewhere. Okay. So yay, we sort of have an understanding, I guess geometrically even, of what these numbers are by looking at them on a number line. Now, to understand complex numbers geometrically, we can do it, but because each complex number has two independent parts to it, we're going to need something two-dimensional to represent it. Okay? And this two-dimensional grid that we're going to talk about is called an Argand diagram, named for a mathematician by the name of Argand. The horizontal axis is going to be the real axis, and the vertical axis is going to be the imaginary axis. So in a lot of ways, it's going to look really similar to any normal graph you guys are comfortable with, but instead of labeling these axes x and y, we're going to be labeling these the real axis and the imaginary axis. And so if you wanted to plot the complex number 3 minus 4i, you would sort of imagine going 3 in the real direction and -4 in the imaginary direction. And this point right here would sort of graphically represent 3 minus 4i. Sometimes people will draw an arrow to it. It can be done either way. Okay. So -1 plus 6i on an Argand diagram would be us going backward 1 in the real direction, and then in the imaginary direction going up 6. 1, 2, 3, 4, 5, 6. So at this point here, again, you can draw the arrow or not. -1 plus 6i, that's what that would look like on an Argand diagram. And this may seem like a bit of an arbitrary definition, like maybe this was just this guy Argand, making something up to get his name on something. No, it turns out that there's a value for this, and we will learn that in time. We're going to learn a little bit of it soon, and more of it we'll have to wait until a little bit later. So now that we can see that these complex numbers can be graphed on an Argand diagram, you might notice that, you may or may not, I think I want to point out to you that the way that we generally think about complex numbers, the way that we think about them as 2 plus 4i, is very rectangular. It's very, very Cartesian. But with some creativity, we can also think about complex numbers in a more circular or polar manner, and that allows us to bring some trigonometry into it. And you might be wondering, why would you ever want to bring trigonometry in? It's because it allows us access to some really, really powerful tools down the line. But to do all this, we're going to need some new vocabulary and some new notation. So the definitions that I have, the new vocabulary, is first the word modulus. Okay? The modulus of a complex number z, which is denoted like this. It looks like absolute value. So the modulus of a complex number, so this does not mean the absolute value, the modulus of z is the distance from the origin to the location of the number on the Argand diagram. So it's a little bit of a concept of distance or length. Okay. The second definition is argument. Okay. The argument of a complex number z, which is denoted arg, so arg of z, is the angle that the arrow drawn on the Argand diagram makes with the positive real axis. Now, those concepts may be a little bit unclear, so I want to go through a fairly simple example to sort of help you make sense of that. All right, so first, let's draw 4 plus 3i on an Argand diagram. And I'm going to kind of shift my Argand diagram a little bit. I can tell that this is in the first quadrant, so I'm going to sort of focus my graph on the first quadrant. So real and imaginary. So if I was going 4 in the real direction and 3 in the imaginary direction, and I got, this kind of point here, 4 plus 3i, and then if I, drew this arrow that I've been talking about, now I need to use my knowledge of trigonometry to find the magnitude and the argument. Okay, well, to use trigonometry, I really need sort of like a triangle here. So what we're going to do is sort of, imagine that we have this right triangle that we do. We knew that the real part was 4 and the imaginary part was 3. And so we can pretty quickly find that the modulus will be the square root of 4 squared plus 3 squared. It's actually a Pythagorean triple, so that's going to end up being 5. And then for the argument of 4 plus 3i, we're effectively looking for this angle here. We're looking for the angle that this thing makes with the positive real axis. Okay. Well, that's just going to be a tangent computation. We can do the inverse tangent of the opposite side over the adjacent side, so the imaginary part over the real part. And I got this to be 0.644. So there's kind of this idea that we can talk about this complex number as either being 4 plus 3i, and this is sort of like our rectangular or our Cartesian form. And we can also talk about this complex number as being a complex number that has a modulus of 5 and an argument of 0.644. We're going to need to come up with some sort of better notation for that, but these are both representations of the same idea. Now you might kind of wonder, like, why are we making life difficult for ourselves by coming up with some completely new and different way of measuring things, right? And I think something that I might mention is that when you are like walking somewhere and you're driving somewhere and you're taking city streets, if you knew that it was 4 blocks this way and 3 blocks this way, it would make sense to sort of describe it as go 4 this way, go 3 this way, and yay, there you are, right? But if you had like a helicopter, or if this wasn't city streets, if this was, you're out in the ocean or on a lake and you need to get from the position that you're at to here, no one would describe that and say, oh yeah, just go 4 miles directly east and then 3 miles directly north and then there you are. You would sort of describe, hey, you can actually just go directly there. What you want to do is you want to go, 5 miles or kilometers or whatever, want to go 5 distance that way. And the bearing that you want to take, the direction that you want to take is an angle of 0.644 radians north of east. So there's kind of this idea that we can see and appreciate that there might be 2 different ways of describing how to get from the origin to this point. And what we're doing here with complex numbers is we're sort of leveraging that difference. For any of you that have actually started looking at the vectors lessons, you'll notice that there's some parallels here. There are some things that are happening that are similar between vectors and complex numbers. You're not going to need to know any of the vector stuff, but if you have, it's neat to notice. Now, in the last example, when I needed to compute the modulus and the argument of a complex number, I drew an Argand diagram. And I'm going to give you some formulas now, but I want to point out that it is always helpful to draw the Argand diagram before just using these formulas. There are some things that can go a little weird, and so I think it's really important. The Argand diagram does not take you very long to do, and it really makes it possible for you to sort of check your answers on the modulus and the argument and make sure that they're making sense. So something that I hope you noticed on the previous example, we can always find the modulus by just doing the square root of the real part squared plus the imaginary part squared. We're really just using sort of the Pythagorean theorem there. The argument, though, is a little bit more complicated. For the argument, you notice that I did the inverse tangent of the imaginary part over the real part. Okay? But the thing about inverse tangent is, when you use your calculator for it, inverse tangent is always only going to give you an answer that's in the first or fourth quadrants. So what happens when your complex number is over here in the second or third quadrants? Okay? When that happens, you need to do the inverse tangent and then add pi to it. So that if you got the first quadrant version, you can add pi to get the third quadrant version. If you got the fourth quadrant angle, you can add pi to get the second quadrant angle. And so what you want to do when you're doing this is you first draw an Argand diagram, then you do the modulus computation, because that one's always going to be correct. And then after that, you do this inverse tangent and look at your diagram to see if you need to add pi or not. So we're going to go and go through that in this example here so you can sort of see this process in action. Of course, if you've got a good sense for it, you can try this one on your own. So part A, we want to draw this on an Argand diagram. So we draw it 1, 2, 3, 4, 5, 1. Okay, so we sort of got that guy right there. Okay, now we want to use the formulas above to find the modulus and the argument. Well, the modulus should be the square root of negative 5 squared plus 1 squared. Notice that when I'm doing this b, I'm not doing I. I'm just doing the coefficient that's in front of it. Okay, so this is the square root of 26. So yay, we found that. And then the argument, when I do the argument of negative 5 plus I need to do the inverse tangent of 1 over negative 5. And when I do that on the calculator, I got negative 0.197. And this is in radians. So what effectively happened here is that when I did this, negative 0.197, that's like that argument right there. Okay? What we want is pi more than that. So I need to take this and add pi to it so that I'm going to get the proper angle. Remember that we said in the previous example that the argument is always the angle made with the positive real axis. So you're not interested in this angle here. You're interested in the one that's made with the positive. It's like you're moving on a unit circle. Okay? So when I add pi to this, I find that this argument is 2.94. Okay? Now, part C is something that you haven't seen coming. Okay, I didn't talk about this in the previous one. Part C says, let R be the modulus that you just computed, and let theta be the argument that we just computed. Okay? Now, in part C, I want you to compute what is R times the cosine of 2.94, and what is R times the sine of 2.94. What do you see when you do those? You should have found that these were negative 5 and 1, right? And what's amazing is this right here is literally the real part of z, and this is the imaginary part of z. So we're going to use these ideas of r cosine theta and r sine theta to come up with a notation that we can use for this polar form. By the way, the numbers that you got here might not have been exactly these, especially if you were using the rounded off values. If you use the value stored in your calculator, it should be much closer. So at this point, I sort of want to pause for a moment and sort of formalize the two different forms of a complex number that we have. Cartesian form, or rectangular form, is the one that we were sort of comfortable with before. The z is x plus yi. It's just a real part plus an imaginary part times I. Okay? If you have a complex number in that form and you want to change it into the polar form, what you do is you find the modulus, and then you find the argument by the same methods that we did in the previous one. So we draw an Argand diagram, and then we sort of use that to check our tangent computation, and if necessary, we add pi, basically if it's in the second or the third quadrant, and that's it. So Cartesian form is great. It's really helpful. It makes it really easy for us to add and subtract complex numbers. And we're going to be learning a lot of tools as we move further into this chapter about how polar form can be used to do some really neat things. In fact, the next two examples might sort of hint at something. I'm not going to talk a whole lot about it, but it may be something that we see sort of show up later. Now, polar form, I need to spend a little bit more time sort of explaining what's happening here. The form that we use for polar form is this right here. Z equals R cis theta. So R is just the modulus that we found, and theta is just the argument that we found. Now you may be wondering, like, what is this cis about, right? Well, the cis here stands for cosine I sine. And so cis is basically shorthand for us saying R times the quantity cosine theta plus I sine theta. So rather than having you write out, 5 cosine pi plus I sine pi, like instead of having to write that whole thing out for the polar form of a complex number, you can instead just do 5 cis pi. And you just need to remember that anytime you see this concept of cis notation, you can expand that out into this. Okay? Now, if you ever wanted to take something that was in polar form and change it back into rectangular or Cartesian form, it's actually really easy. You just do this computation. You do r times the cosine of the angle, and that becomes your x component, your real component, and you do r times sine theta, and that becomes your imaginary component. Now the rest of the video is just going through examples of working through these two different forms. And like I said, there's a little bit of neat hidden knowledge in the next two examples. If you notice it or see it, that'll be exciting. It might be something you'll get a chance to show sometime later. If you don't notice those things, that's fine. I'm going to make it really explicit when we get there. All right, so this next example, I want us to consider the complex number r equals 4 cis pi over 3. So part A, I want us to take this and convert it into Cartesian form. So if you feel like you got a good sense for how to do that, go ahead and pause the video and do that now. If you'd like to see it done, then stay with me. So we noticed in the previous slide, or maybe we don't even say that, maybe what this thing means, remember, is it means that our complex number is 4 times cosine pi over 3 plus I sine pi over 3. So converting this thing into Cartesian form really just means doing this. So I've got 4. The cosine of pi over 3. Pi over 3 is the high one, so the cosine would be a half, plus I times the sine of pi over 3. Again, we're sort of thinking about our unit circle. Pi over 3 is up here, so sine's the tall one. That's the square root of 3 over 2. So when I distribute the 4 into this, I'm going to find that r is 2 plus 2I root 3. By the way, I don't think I mentioned this in any of the previous videos. The reason I never put an I after a square root is it's just too easy for me to accidentally make this bar a little too long and for it to feel like the I is underneath the square root. And we don't want to deal with that. So I tend to put the I here and not after a square root. All right, so part B, compute r squared and write it in Cartesian form. Okay, so for part B, I'm being asked to take this thing that I just got, 2 plus 2I root 3, and square it. Now remember that what that means is it means I need to do 2 plus 2I root 3 times 2 plus 2I root 3. So if I go and sort of like FOIL this thing out, 2 times 2 is 4, and then here I'm going to get 4I, let's see, not 4I root 3, but, 4I root 3. Here I'm also going to get 4I root 3, and here is where I get 4I squared root 3 squared, which just means another 3. But we know that this I squared is just going to turn into a negative, so that's minus. So for the real parts, I have 4 minus 12, so that's negative 8, and here I have 8I root 3. So we've got our answer for part B here. We've got our answer for part A up here. Now for part C, we're being asked to graph r squared on an arcane diagram and then convert it to polar form. Okay. So on an arcane diagram, negative 8, 8 plus 3, 8 plus I root 3, so negative 8, 2, 4, 6, 8, and then 8 root 3. Root 3 is like 1.7-ish, so we're looking at, I don't know, like 16-ish here. So 1, 2, 2, 4, 6, 8, 10, 12, 14. I guess it's not actually quite 16. We don't need to be exact here. We're getting a sense for where this thing is so that we know how to find our argument. So remember, the modulus is going to be this length here, and the argument is going to be this angle here. So to find the modulus, negative 8 plus 8I root 3, I'm going to do the square root of negative 8 squared plus 8 root 3 squared. So this is 64 plus 64 times 3, which is 192. And when I add those things up, I get the square root of 256, which is 16. Okay. For the argument, I need to do So the argument of r squared. Just noticed it's a little bit weird that I called this r, because r is usually the thing we use for this. I'm sorry if that caused any confusion. So anyway, to compute the argument of this new squared complex number that we're working with, I need to do the inverse tangent of the imaginary part over the real part, which basically means the inverse tangent of negative root 3. Now, I don't know if you recognize it or not, but this is actually a unit circle value, right? Turns out that this is either negative pi over 3 or it's 2 pi over 3, because in both of those cases, the sine of the angle that we're looking at is root 3 over 2, and the cosine of the angle that we're looking at is 1/2, and so the 2's will cancel, and you're just left with like the root 3 over 1, and so down here, negative pi over 3, and up here, positive 2 pi over 3, are sort of the two places where that thing happens. The angle here that clearly makes sense for us is 2 pi over 3. And the last thing we were asked to do in this problem was to rewrite this in polar form, right? So our original complex number in polar form was 4 cis pi over 3, and then when I squared it, it became 16 cis 2 pi over 3. Now, like I said before, there's definitely a neat sort of connection to be made here. If you see it, wonderful. If not, no big deal. And remember, even if you do see something, it doesn't mean it's necessarily proved and true. It just means you've seen a pattern. And so we may be interested at some point in sort of proving that pattern. If you don't know what I'm talking about, don't worry about it. I'll make it really clear at some point in the future. All right, so I've got another problem here that's fairly similar to the last one. We're not going to be squaring this time. We're going to be multiplying instead. I'd highly recommend that you pause the video and try this one on your own. Some of the examples in the assignment for this evening are going to be really similar to this. So give yourself a chance to try it. So part A, I need to sketch these things on an Argand diagram, right? So for z, root 2 plus I root 2. Root 2 is like 1.4. So right here is about where z is. Okay. And I don't always like to do them on the same Argand diagram. Sometimes I feel like it makes it a little bit harder for me to sort of see what's happening. So I'm going to do the other one over here. 3 root 2, that's 3 times 1.4, so it's a little bit bigger than 4. So a little bit bigger than 4, a little bit bigger than 4. So I've got kind of like this guy down here. This is w. All right, so next I need to write these things in polar form. So to write them in polar form, I'm going to need to come up with their new components. So for this one, I'm going to need to do the modulus, the square root of root 2 squared plus root 2 squared. That's 2 plus 2, which is the square root of 4. So this is 2. So the modulus of this is 2. For the argument, I need to do the inverse tangent. Well, wait a minute. Do I really need to do inverse tangent? Like, this is root 2 and root 2. Hopefully you guys can see this is like a 45-degree angle, right? So I suppose I could write it down. The inverse tangent of root 2 over root 2 is going to be pi over 4. Okay? So especially when these are unit circle values, these are often things we can get pretty quickly. Last thing I needed to do here was actually write it in polar form. So I want to write that the complex number z can be expressed as 2 cis pi over 4. Okay. For w, I need to find the square root of 3 root 2 squared plus negative 3 root 2 squared. You might have noticed this negative here really doesn't matter because it's going to get squared. I don't know that it's necessary to write it here, but it's just a good idea to be in the habit because other places the negative really does matter. So as I work through this will be the square root of 18 plus 18, which is the square root of 36, which means this modulus is 6. And then similarly for the angle down here, I'm going to do the inverse tangent of the imaginary part over the real part. But again, this is This is inverse tangent of -1. This is another unit circle value. This is just negative pi over 4. So writing this one in polar form is going to be 6 cis negative pi over 4. Okay, now part C, we're supposed to take z and w and multiply them. That's what this is asking for. So we need to multiply them together in Cartesian form and then sketch it on an Argand diagram. Okay, so let's do that. For part C, I'm supposed to do z times w. So that's going to be root 2 plus root 2I times 3 root 2 minus 3I root 2. So when I go through and multiply this out, these ones give me 3 times 2, which is 6. This times this is going to get me negative 6I. This times this is going to give me positive 6I. Oh, so that's neat. Those drop out. And then at the end here, I'm going to have minus 6I squared. Well, the I squared is going to become a -1, which will turn this positive. So it looks like z times w is going to be 12. Now it asks me to graph that in an Argand diagram, and this may seem silly, but it's going to be valuable for what's coming next. The Argand diagram for 12 is just, hey, look at me, I'm 12. Right? Like, there it is. Now, the reason that this is valuable is that in part D, we're asked to take ZW and convert it into polar form. Okay? But based on this thing, can we already tell what the magnitude of this is, what the distance is from the origin over to here? Yeah, I mean, it's 12. It's not up at an angle where we have to compute a modulus for this thing. We can already tell that this is 12. Can we tell what the argument of this thing is? Remember, we're not looking at this, right? Can you tell what the argument of 12 is? Can you tell what the angle that it makes with the positive real axis is? Yeah, it's 0, right? This is 12 cis 0. And that's essentially the end of the problem. For those of you that are sort of maybe curious about what's happening, behind the scenes on these things, we just took a complex number that was 2 cis pi over 4 and multiplied it by a complex number that was 6 cis negative pi over 4. And what we got out was 12 cis 0. So again, you may think that you're noticing something. It may be different from what you did on the previous example. We're eventually going to come back and formalize a lot of this. For today, none of this thought stuff at the end is really going to matter. We're really just practicing this polar form before we move forward with other things. I hope all of that made sense. As always, if you have questions, please reach out. I wish you the best of luck as you work through this assignment.